Hi there everybody, welcome to iTTV. For today's lesson, we will be looking at oxidation and reduction. So today's title of the lesson will be about redox reactions and the reactivity series. So what are the learning outcomes for today's lesson? Well, we'll be basically looking at the reactivity series, how to determine the position of certain elements in a reactivity series, for example, carbon and hydrogen. And then we will look at applications of the reactivity series as well. So, what is the reactivity series? It is a series of metals arranged according to their chemical reactivity with oxygen. So, a more reactive metal can reduce the oxide of a less reactive metal. Metals below carbon are extracted from their ores by heating the metal oxide together with carbon. So metal oxide will react with carbon to produce metal as well as giving out some carbon dioxide. If you look at the reactivity series on the left part of the slide, as we proceed upwards, the metals tend to be more reactive towards oxygen. So how the scientists actually came up with the reactivity series was they tested each element's reactivity towards oxygen. So oxygen is the parameter to determine the position of the metals in the reactivity series. And it's very, very important for students to understand that metals below carbon are usually extracted from their ores by simply heating the metal oxide together with carbon, because carbon will then be able to reduce the oxide of the less reactive metal. Metals above carbon in the reactivity series are extracted from their ores by electrolysis of the molten compound. Example, aluminium is extracted from bauxite, which is aluminium oxide, by electrolysis. So just now we looked at how to extract metals below carbon in the reactivity series. Now, how do we react metals above carbon? It would be through a simple process of electrolysis, because if we were to heat these metal oxides with carbon, carbon will not be able to reduce the metals from their oxides. So, the empirical formula of oxides of metals above hydrogen is determined by heating the metal in a crucible to allow the metal to combine with oxygen in the air. For example, potassium, calcium, and magnesium. The empirical formula of oxides of metals below hydrogen is determined by passing dry hydrogen gas through the metal oxide placed in a combustion tube. Example will be iron 3 oxide, stannum oxide, lead oxide, copper 2 oxide, and silver oxide. So this slide is just to show you that there are a few ways to determine the empirical formula of oxides, be they above or below hydrogen. Empirical formula is the simplest molecular formula of a compound. Let's look at a simple experiment to investigate the reactivity of some metals with oxygen. The hypothesis would be, the more reactive the metal, the more brightly it will burn in oxygen. The manipulated variable here will be the type of metal, while the responding variable will be the brightness of the flame or the reactivity of the metal. Controlled variables would be the mass of metals and the mass of potassium manganate 7. Apparatus needed will be like the retort stand, Bunsen burner, etc. Materials would be potassium manganate 7 solid, metal powder, and glass wool. So let's have a look at the setup of the experiment. As you can see in this vertical test tube, we add potassium manganate 7 solid as the source of oxygen when it is heated. So oxygen will react with the metal powder in a crucible, but the metal powder is also heated at the same time. So we will see how bright the metal powder actually burns in oxygen. The more reactive the metal, the more brightly it will burn in oxygen. Let's look at some samples of results. For For example, if the metal is magnesium, it will glow with a very bright flame, and the color of the residue, which would be the metal oxide, would be white in color. That would be magnesium oxide. Zinc would glow with a bright flame. When hot, it's yellow. When cold, it's white. That is zinc oxide. Iron will glow with a bright glow, and the color of iron oxide would be brown. Now, how about lead? Lead glows moderately bright glow. When hot, it's brown. When cold, it's yellow. That's lead oxide. How about copper? Copper only glows faintly, and the color of copper oxide would be black. So this tells us the color of the metal oxides as well as the reactivity of the metal based on how brightly it burns in the presence of oxygen. And the source of oxygen here is when potassium manganate solid was heated. Now let's look at another experiment to determine the position of carbon in the reactivity series of metals. The apparatus and materials are shown in the slide. The note is, if carbon is more reactive than metal M, then it will reduce the metal oxide to metal M. As shown in the equation, carbon reduces metal oxide to metal M, and in the process producing carbon dioxide. There will be no reaction if carbon is less reactive than metal M. And you can see the setup for the experiment that carbon powder is heated together with metal oxide, and M refers to the metal. So this experiment is just to help to determine the position of carbon in the reactivity series. If carbon is more reactive than a particular metal, it will surely be able to reduce the metal oxide to metal. And in the process, carbon will be oxidized to carbon dioxide because this is a redox reaction. Reduction and oxidation happens at the same time. Carbon oxidized to CO2, metal oxide would be reduced to metal M. So if carbon is less reactive than a particular metal, there will be no observable change. So let's look at some observations. If carbon is reacted with magnesium oxide, there should be no change because magnesium is more reactive than carbon. If carbon is reacted with aluminium oxide, there would also be no change because aluminium is more reactive than carbon. But if carbon is reacted with zinc oxide, there would be a bright glow in the crucible because carbon is more reactive than zinc. If carbon is reacted with copper oxide, there would also be a bright glow because carbon is more reactive than copper. So the chemical equations as shown would be that because carbon is more reactive than zinc, it's able to reduce zinc oxide to become zinc metal, and in the process, carbon is oxidized to carbon dioxide. Secondly, if carbon, because it is more reactive than copper, it's able to reduce copper 2 oxide to copper metal, and in the process, carbon is oxidized to carbon dioxide. So the conclusion would be that the position of carbon is before zinc and copper in the metal reactivity series. Magnesium, aluminium, carbon, zinc, hydrogen, iron, stannum, lead, copper. So as we proceed more to the left, the metals are more reactive. Let's move on to another procedure. Another example whereby we react magnesium and carbon dioxide. The procedure was we fill a glass jar with carbon dioxide and we burn magnesium with a Bunsen burner. When magnesium starts burning, we put it into the gas jar and we observe. So the observation would be, there are 3 observations. Firstly, magnesium continues to burn in carbon dioxide gas. Secondly, white residue is formed. And thirdly, a black powder is found inside of the gas jar. So, what is the chemical equation involved? And thereby this helps us in our conclusion would be that magnesium is able to reduce carbon dioxide into magnesium oxide as well as carbon. So therefore, what happens is that magnesium is able to reduce carbon dioxide because magnesium is more reactive than carbon. Magnesium is at a higher position in the reactivity series than carbon, so it's able to reduce carbon dioxide into magnesium oxide, which is the white residue formed, and the black powder formed is the carbon powder. So magnesium continues to burn in carbon dioxide gas because there is a reaction happening. There is a reduction process happening. So this additional experiment is just to further confirm and verify the position of magnesium and carbon in the reactivity series, and this confirms that magnesium is more reactive than carbon. Next up, let's look at another experiment to determine the position of hydrogen in the reactivity series of metals. So we see a vertical test tube whereby dry hydrogen gas is pumped into the tube. We have X oxide which is heated, and we have hydrogen flame at the end. So the manipulated variable will be the type of the metal oxide, while the responding variable would be the presence of a bright glow. Controlled variables would be the mass of the metal oxide. Precaution here will be pass hydrogen gas to remove the air from the combustion tube before heating to avoid explosion. And upon completing the experiment, the position of hydrogen in the reactivity series would be potassium, sodium, calcium, magnesium, aluminium, carbon, zinc, hydrogen, iron, stannum, lead, copper, silver, and gold. And it's more reactive as it proceeds to the left. So this experiment is actually quite dangerous and will not be done because hydrogen is very combustible. So if hydrogen actually reacts with oxygen, there could be an explosion. So therefore, there was a need to pass hydrogen gas in the tube to remove the air first. So, what are the applications of the reactivity series? Firstly, to predict whether a metal will reduce the metal oxide of another metal. For example, if metal X is more reactive than metal Y, and given an equation, X, being more reactive, will be able to reduce the metal oxide of Y, and this will produce XO as well as Y. But if we try to react metal Y with the oxide of metal X, there would be no reaction. So, secondly is to determine the method used to extract a metal from its metal ore, which could be an oxide, sulfide, or carbonate of the metal. So, in conclusion, we can see that the more reactive metals, more reactive than carbon, such as potassium, sodium, calcium, magnesium, and aluminium, they are extracted through electrolysis, while those metals less reactive than carbon, such as zinc, hydrogen, iron, stannum, lead, copper, and silver, they can be extracted from their ore by heating the metal oxide from the metal ore with carbon, known as coke in industry. So, the reactivity series is important because it gives us two applications. Firstly, it allows us to predict whether a metal can reduce another metal oxide, and secondly, is able to help us determine the specific method, either electrolysis or just by heating the metal oxide with coke to successfully extract a metal from its ore. Now, please note that carbon is widely used to extract a metal from its ore in a blast furnace. Metals which are more reactive than carbon, for example potassium, magnesium, they are not used. Reason being, carbon will not be able to reduce those metal oxides to metal. Okay, let's look at our first question for today. Predict whether a reaction will occur, ticking correct if a reaction happens and wrong if no reaction. So, would zinc oxide react with hydrogen or iron trioxide react with hydrogen? Steam plus zinc, magnesium oxide plus carbon, magnesium plus carbon dioxide, sodium plus water, aluminium plus lead oxide. So students, what do y'all think are the answers for these sub-questions? You need to have knowledge of the reactivity series to answer this question. Have a thought about it. As mentioned, to answer these questions, you need to have knowledge of the reactivity series, which you have to memorize. So let's look to the board to have a better understanding of this question. As mentioned just now, the reactivity series starts with potassium being the most reactive metal, followed by calcium, magnesium, aluminium, and carbon would be here. Below carbon would be zinc, and you have hydrogen here, iron, stannum, we have lead, copper, mercury, silver, and lastly gold. So this is the reactivity series whereby as we proceed up, the reactivity increases. As we move up, reactivity increases. So let's look at our first sub-question. Would zinc oxide react with hydrogen? Let's look at the positions in reactivity series, because hydrogen is here, position of hydrogen, and zinc is above. So because zinc is more reactive than hydrogen, so obviously hydrogen will not be able to reduce zinc oxide into zinc metal. So the answer for this will be no reaction, because zinc is more reactive than hydrogen. Secondly, we have iron 3 oxide reacting with hydrogen. Now this time, let's look at the position of iron. Iron is here and hydrogen is above. So we can see that hydrogen is more reactive than iron. So hydrogen is able to reduce iron trioxide. So therefore, a reaction will happen. Thirdly, steam and zinc. Steam and zinc. Would this reaction happen? Now let's look at the position of zinc. Zinc is here and hydrogen is here. Would zinc be able to reduce the oxide of hydrogen, which is considered as water? Zinc is more reactive than hydrogen, so yes, zinc is able to reduce the oxide of hydrogen. So also, yes. Next up, we have magnesium oxide as well as carbon. Let's look at their positions. For magnesium, the position of magnesium is here, and carbon is here. Magnesium is more reactive than carbon, so carbon certainly will not be able to reduce magnesium oxide into magnesium metal. So the answer for this? No reaction will happen because magnesium is more reactive than carbon. So carbon cannot reduce magnesium oxide. Next up, we would have magnesium as well as carbon dioxide. This is different. Now, magnesium is more reactive than carbon as mentioned. So magnesium, yes, will be able to reduce carbon dioxide. Magnesium is able to reduce the oxide of carbon. Yes. Next up, let's look at sodium and water. Would a reaction happen? So let's look at the position of sodium here. And hydrogen will be here. Because sodium is so much more reactive than hydrogen, so sodium is certainly able to reduce the oxide of hydrogen, which is water. So the answer, yes, we would see a reaction happening. Next up, last one would be aluminium and lead oxide. Would a reaction happen? Let's look at the position. We have lead here and we have aluminium here. Aluminium is so much more reactive than lead. So yes, aluminium is able to reduce the oxide of lead into lead metal. So a reaction will also happen. So this is how we answer questions with regards to the reactivity series. So you need to memorize the reactivity series. Now, let's look at extraction of iron from iron ore. In iron ore, we call it a hematite. It contains iron trioxide, while other examples of iron ores would be magnetite that contains another type of iron Ch.04. So carbon is used as a reducing agent. A mixture of iron ore, coke and limestone, which is known as calcium carbonate, is heated in a blast furnace by pumping hot air from the bottom of the furnace. A diagram of the blast furnace is shown later. So as you can see here, the blast furnace is a large contraption whereby three very important components are added at the top. We have the iron ore, which is known as the hematite. We have coke and limestone, where very hot air is pumped from the bottom of the blast furnace. And even below that, you see slag being collected at one end. Slag is a mixture of unwanted materials, and molten iron is collected on the next side of the blast furnace. And that is how extraction of iron happens. Now, what are the reactions happening? This is very, very important because calcium carbonate, which is the limestone, under heat will break down into calcium oxide and carbon dioxide. Besides that, the coke, which is carbon, will be oxidized to produce carbon dioxide. So those two methods are to produce carbon dioxide. What happens to the carbon dioxide? It can actually be reacted with further carbon to produce carbon monoxide. And this is the reduction of carbon dioxide to carbon monoxide through its reaction with more coke. Now, what happens to iron trioxide? It will react with carbon to produce iron as well as carbon dioxide. Essentially, iron trioxide can also react with carbon monoxide to produce iron and more CO2. So those two are methods to reduce iron trioxide. So iron trioxide is the hematite ore, and carbon, because carbon is more reactive than iron, so carbon is able to reduce the oxide of iron into iron metal, and in the process, carbon becomes oxidized into carbon dioxide gas. So the blast furnace process, as you can see, produces vast amounts of carbon dioxide, which is very bad for our environment because it contributes to enhanced greenhouse effect and global warming. Next up, that was about extraction of iron from iron ore. Let's look at the second application of the reactivity series knowledge, which will be extraction of tin from tin ore. So the tin ore is known as cassiterite, and cassiterite containing tin 4 oxide. So tin is extracted by heating a mixture of concentrated tin ore and coke in a furnace. The reaction that happens would be tin oxide can react with carbon to produce tin and carbon dioxide, or tin oxide can also react with carbon monoxide to produce tin and carbon dioxide. So as you can see, because carbon is also more reactive than tin, so carbon is able to reduce the oxide of tin into tin metal, and in the process, carbon becomes oxidized into carbon dioxide gas. So both ways are how to extract metals from the oxides by heating with carbon. And this process can only be done for metals which are less reactive than carbon, like iron and tin. Next up, let's look at the thermite process, and this involves the reduction of iron trioxide by aluminium. Molten iron is produced because the reaction is highly exothermic. This process is used for welding steel objects. So this is another method to actually extract iron from its oxide, but this time we don't heat with carbon, but we actually heat with aluminium, and this process produces also molten iron, and we use this process for welding. Now, if you look at the diagram, there is in the filter paper a mixture of barium peroxide and magnesium powder, and we stick a wick in, which is actually a piece of magnesium ribbon. So, besides that, in the component, you also see aluminium powder and iron trioxide. And what we do is that we actually will heat the magnesium ribbon. What is the function of this magnesium ribbon? It is to act as a wick. And what is the function of the barium peroxide, which is added together with the aluminium powder and iron trioxide? It's basically to produce a very high temperature. As mentioned earlier, that this reaction is highly exothermic. So as you can see, because aluminium is more reactive than iron, so aluminium is able to reduce the oxide of iron into iron metal, and in the process, aluminium becomes oxidized to aluminium oxide. Now, let's look at a comparison of the reactivity series and the electrochemical series, because today's lesson basically focuses on the reactivity series, and we notice that the position of hydrogen in the reactivity series is different from the electrochemical series. Okay, please take note that in the reactivity series, the position of hydrogen is between zinc and iron, but in the electrochemical series, the position of hydrogen is between lead and copper. So that is the difference. And in the electrochemical series, there is no carbon added into the series. So those are the two major differences. The electrochemical series has no carbon, and the position of hydrogen in both series are different. So why do we need to have these two series? In the reactivity series, elements are arranged according to their reactivity towards oxygen, and it is used for predicting the reactivity of an element towards oxygen, or to choose a suitable method for extraction of metal from metal ores. Elements are arranged according to their ability to form positive ions in the electrochemical series, and the electrochemical series is used for choosing a suitable sacrificial metal for corrosion, or to determine chemical cells to find out which is the positive or negative terminal. Also for electrolytic cells to select discharge of ions, or perhaps even in displacement reaction. So you can see the applications of the reactivity and the electrochemical series, that the reactivity series is so important because we can choose either an electrolysis method or just heating with carbon as a way to extract metal from the metal ores. Besides that, for the electrochemical series, it's more important for predicting which is the positive or negative terminal for a voltaic cell, and it's also important for the electrolytic cell as well, because we would want to know which ions will be selectively discharged at which electrodes. So let's look at question 2. The diagram shows the extraction of iron in a blast furnace. What is substance X? A. Coke, B. Silver, C. Aluminium, D. Vanadium 5 oxide. So students, what do y'all think is the answer for this question? Let's ponder for a while about this. Now, this one actually is a little bit of memory work because remember we talked about the blast furnace, that there were 3 main ingredients to be added at the top part of the blast furnace. And one of them will be, of course, we need the iron ore. That's our main raw material. And secondly will be limestone, which is calcium carbonate. The third item, well, as I said, memory work, is none other than coke, because coke here will be carbon. And carbon is needed to reduce the oxide of iron into iron metal, because carbon is more reactive than iron. So the answer, everybody, will be A, coke. So let's wrap it up with a short recap for today's lesson. We looked at the redox and reactivity series, as well as a series of experiments to predict the position of metals in the reactivity series. And secondly, we looked at applications of the reactivity series. For example, we wanted to know how reactive a metal is with regards and with relative to each other, and we're able to choose a particular method to actually extract a metal from its ore. Should we choose electrolysis, or should we just heat the oxide with carbon to extract the metal from its ore? And thirdly, we look specifically at the extraction of 2 metals, which would be iron and tin. So we looked at application of reactivity series in the extraction of iron as well as tin, further looking at the termite process as well. So that's the summary for today's lesson. Well, that's the end of today's lesson. Thank you so much for watching iTTV. We look forward to seeing you all again the next time. Thank you and have a wonderful day.